Well, Monte Carlo is unbiased. Law of large numbers, Chebyshev, various ways of showing that the expected value of the Monte Carlo method is the right price. They're unbiased estimators of what we're trying to estimate. And so if we go back to the formula, it has to be the fact that this estimate of the expected value of A star is the same as is also the right price. In other words, even though I'm making an adjustment in the control variate method, it's an adjustment whose expected value is 0. So it doesn't change the mean. The expected value of A star is the same as the expected value of the Monte Carlo, which is A. So right off, I have an adjustment procedure that doesn't create any bias for me. It leaves the mean of the distribution alone. Now the question is, what about the variance? Well, we have a variance of a sum as the sum of the variances and a covariance adjustment. And that's what I've developed here. This is a standard variance. So what it says is that the variance of A star, my estimated control variate estimate, if I go back, the variance of A star should be the variance of the Monte Carlo here. Of course, the G is just a constant. I can ignore that. So I can really, for the purposes of variance, throw the G away. It's just a number. And think of this as AMC minus GMC. So the variance of that is the variance of A plus the variance of G minus twice the covariance term. And that's just exactly the formula we see here. It's the variance of A plus the variance of the G estimate minus twice the covariance. So if the Monte Carlo estimates are highly correlated, the A star will have a smaller variance than the Monte Carlo estimate. And let's see why that is true. If I just rewrite this formula in a more common notation, I could say that the variance of A star is equal to sigma A squared plus sigma G squared minus 2 correlation of AG sigma A sigma G. So now I'm just eliminating the MC superscripts just for simplicity, but this is the variance of A, the variance of the G estimate, and then I've rewritten the covariance between the A and the G estimates as the correlation in those estimates times their standard deviations. So if I now write this as sigma A squared plus sigma G you can see that because of the factor of 2, if sigma G and sigma A are roughly the same size, even if the correlation is a little bigger than a half, because I have a 2 being multiplied by it, this is most likely going to be negative. And that's the point. The point is that it's in many applications, one will have the situation where if I take twice the correlation times the standard deviation of A, it'll exceed standard deviation of G. Even for correlations somewhere around a half, you could have this situation. That makes this entire term negative, which then means that this will be, in fact, smaller than the variance of A. And that's the point. That's how we're improving our estimation. Now, you could argue that we have to do more work. In order to determine A star, we have to value both the geometric and the arithmetic Asian option, whereas if all we cared about was the Asian, we would only need to do one calculation. But the point is that it's often found that control variate improves the accuracy so much that you can get good answers with smaller values of n and therefore get saved work. Or with the same amount of work, same value of n, get significantly better estimates because we've reduced the standard error.